Okay, then hello everyone to today's seminar on interval methods in control engineering. It's my great pleasure to have today Feng as our speaker. He is associate professor at the Tsinghua University in Shenzhen, China. And he's doing lots of research in the area of measurement and control technology. And that's also the domain where he received his bachelor degree in July 2010. Afterwards, he obtained his PhD degree with honor in Barcelona in Spain. Yes, and afterwards he did also some research, say in France, at Centrale Supélec at Paris. And yes, then afterwards in 2015, he joined the institute where he's currently working. And yes, he's a senior member of IEEE and works on fault diagnosis, state estimation, and fault tolerant control. And we're now looking forward to your presentation on set separation and exclusion tendency-based design framework for active fault diagnosis. The floor is yours.
Okay. Thank you to invite me to introduce some of our latest results. Yeah, actually, I working on set-based fault diagnosis, state estimation, and fault tolerant control. I also have some works on interval estimation. But today, my presentation is about active fault diagnosis. Yeah, during the past 3 years, I spent some time on this topic and also supervised several students who work on set-based active fault diagnosis. Yeah, this is the outline of my talk. Yeah, there are 3 parts here. Yeah, and the first part is about an introduction to active fault diagnosis. Here I want to introduce you a classical set separation-based active fault diagnosis method. Yeah, after that, you will be able to understand what I will propose in the following. A new type of methods based on set value observers. Yeah, it is in the part 2. I gave a name to this new type of measures, set separation tendency-based framework. And in the third part, I will make several short conclusions and show you our future work on this topic. Yeah, as we know, fault diagnosis includes 2 classes of methods. The first one is passive fault diagnosis, and the second one is active fault diagnosis. The difference in that active fault diagnosis design input to excite the system to obtain more information for diagnosis, and passive fault diagnosis does not design inputs. So that is the main difference of the 2 classes of measures. And both of them can be divided into stochastic measures and set-based measures. Yeah, in my research, I can say it's set-based active fault diagnosis. Yeah, in this case, we can take advantage of strong robustness of set-based methods, and at the same time, when we design inputs to excite the system, we can reduce conservatism of set-based fault diagnosis methods. So in some sense, this combination, can take advantage of both set-based methods and active fault diagnosis. So that is the motivation for me to do this research. Set-based active fault diagnosis here, I divided them into 2 classes. The first one is design inputs based on set separation. I gave this name by myself. I also call it classical methods. The representative works are Scott 2014 and Raimondo 2016. And during the past 3 years, our group developed a new type of methods for set-based active fault diagnosis. I also gave a name set separation tendency-based active fault diagnosis methods. In the following, I will introduce 2 later works on this topic. Before we enter into the details, I will show you, I will introduce the model, the system, and the basic logic of set-based active fault diagnosis. Here we consider the simplest system. It's real-time invariant system, and we consider a group of fault moves. Here we use the matrix GI to model different actual faults. Yeah, in this model, yeah, X is the state, U is the input, omega is the disturbance, Y is the output, and eta is the noise. Yeah, based on the models, we can obtain a group of set-wise models. Yeah, each of them matches one healthy or faulty mood. Here we also can say that when uncertainties are bounded, disturbance and noises are bounded by isotopic sets, and inputs are conjoined. So this is the basic information for the separation-based active fault diagnosis I will introduce in the following. And in my talk, all the sets are represented in isotopic forms. Yeah, this is a scheme. This scheme is used to introduce the logic of set-based active fault diagnosis. Yeah, we have a plant. Yeah, we inject some inputs into plant, and we can measure some outputs of plant. And we have a group of set-wise models. Each model matched one actual to fault mood in the plant. So yeah, in this case, at each time instant, we can obtain a group of output sets. Yeah, Y hat, capital Y hat, and then we can do for diagnosis tests. At each time instant, we'll test if the output is inside the output sets or not. If it's inside, we keep this output set, keep this mood. If it's outside, we will discard it, remove it. So we repeat this process step by step, till one time instant. When there is only one fault mood left, it means fault is diagnosed successfully. This is the logic of active fault diagnosis. Hey, I want to introduce the classical set separation-based active fault diagnosis methods. Yeah, I take this. I take the first method from the paper score 2014. Yeah, based on logic before, we can imagine that if we can design an n-step input sequence to separate all the output sets, at time instant k plus n, it means if we inject the input sequence into the system step by step, finally we can guarantee that faults will be diagnosed. So this is the logic, and based on this idea, we can formulate a quadratic program. And the objective function is used to measure the energy of the inputs. And here we have two constraints. The first constraint is the set separation constraint. It's used to guarantee fault diagnosis. And the second constraint is the input constraint. It is a hard constraint. So after we solve this optimal problem, we can obtain an n-step input sequence. That is what we want. But here the main challenge is that, how can we solve this optimization problem? In the right side is a figure taken from score 2014. Here it considered five moods, one healthy and faulty moods. It designs a two-step separating input sequence. So we can say that all the output sets are separated from each other. So in this case, the two-step separating input can be used to guarantee fault diagnosis online. In the paper scored 2014, it proposed a solution to solve this quadratic program. Its idea is to transform the original program into a solvable mixed integer program with mixed integer conjoints. This is the idea. And finally, the problem can be solved under the convex framework. But there is a drawback. It is the computational complexity of this method. Because its complexity is related to the number of integer variables. The number of integer variables exponentially increase with respect to the number of faulty moods, the length of input sequence, and the system dimension. Yeah, here I show you an example. Yeah, I just want to, I mean, it's not a rigorous illustration. Yeah, I just use this simple example to show you, give you an expression on its computational complexity. Yeah, here we only consider 2 inputs, 2 states, and 2 output example, and we change the number of moves from 2 to 6. Yeah, when we have 2 moves, we only need 0.47 second to separate the 2 output sets. But if we increase the number of moves from 2 to 6, in this case, we need 33,000 seconds to separate all output sets. So I think based on this example, we can have an impression on its computational complexity. Actually, in the work scored 2014, it proposed an offline design method. So in this case, I mean, we design the input sequence offline. So in some sense, we move the computational complexity offline, and then we inject the input sequence into a system online to do for diagnosis. So in this way, it's acceptable. Yeah, but in 2014, I mean, we can see the below of the slide. Yeah, Raimondo proposed a closed loop input design method based on set separation conditions. Yeah, its idea is to design input sequence at each time instant online, and then inject the first element of the sequence into a system and repeat the process. Yeah, if we apply set separation methods online, the computational complexity will be a problem for us to apply the methods. So the problem is, how can we reduce computational complexity? Next, I will introduce you our latest results on this program. Yeah, in this part, there are 2 sections. The first section is about framework, observer-based active for diagnosis framework. And then in the second section, I will introduce a new method to optimize the performance. So starting from here, I propose a new idea to overcome in the computational complexity program. As I introduced in the previous part, the origin of the computational complexity is from the set separation conditions. If we want to reduce complexity, we have to discard these conditions. So our idea is that we proposed a new notion. I gave a name, set separation tendency. And then based on this notion, we established a new active for diagnosis framework. I used two figures to show the basic idea. The first block is related to the set separation methods. We design an n-step input to separate all output sets at a time. And our idea is in the second block. Our idea is to design one-step inputs at a time, but we repeat n times until for diagnosis is achieved at a time instant. We design inputs to increase the separation tendency of the 2 sets, step by step, to reach our objective. Behind our idea, a key problem is that how to achieve fast increase of the separation tendency. This figure is used to show our idea. We can see the 2 cells here. If we can minimize the size of cells and at the same time we maximize the synthetic density, in this case we can see that the 2 cells become more separate from each other. So based on this idea, we propose our new framework. But here we also have a new program. We only have one design variable, UK. But we have 2 objectives. How to do it? This is the reason why we introduce set valued observers. Because for our observers, we have 2 parameters. And the first one is observable gains, and the second one is the inputs. Now we have two parameters and two objectives. We use them to reach our objective. Here I show you a scheme of active fault diagnosis framework using a bank of set-value observers. Everything is the same. The only difference is that we use a bank of set-value observer to replace the supervised models. The sensitive details of our process and the size of our process play a very important role in our framework. So we need to formulate its expressions. And here I use psi to denote the sensitive details of our process, and I use phi to represent the size of our process. And here because we use isotopes, so we use Frobenius radius to measure the size of our process. We have two parameters. So both the center distance and the size are related to two parameters. In the following, I will show you our logic to design inputs and observed gains. Here we can imagine that we have two parameters. The ideal way is to design them together at the same time, but it's quite difficult. So in order to simplify the process, I propose a method in the following. But here we need to split the size of the whole output process into two different parts. The first part is only related to observed gains, and the second part is related to inputs. So our logic to design observed gains and inputs are in the following. The first step is that we design observed gains to minimize the first part of the size outputs, because it's only related to observed gain. And in this way, we can obtain an unconjoined optimization program. And finally, we can design the analytical solution of observed gain. Here is the expression. So this means that when we design observed gains online, we only need to make online function value evaluation to obtain its values. After that, observed gains become known. So the size and the sensitive distance of our process is only related to inputs. So in this case, we select the inputs from its conjoined set to maximize the distance. This program becomes a vertex enumeration program. But in general, there is a possibility that there are more than one vertex can obtain the maximum. So in this case, we connect all of them, and we can build a new set. Here I use the symbol U star to denote this set. The third step is that we further minimize the second part of the size outputs. The second part is only related to U, so we select the final optimal FD inputs out of the input set U star. And this program is also an online function value evaluation program. Here I summarize the whole logic before. In general, we have two steps. The first step is to minimize the size of our process. And the second step is to maximize the sensitive distance at the same time. And we can transform this design process into online function value evaluation program and vertex enumeration program. So based on this logic, finally, we can design inputs and observed gains by discarding mixed integer constraints originated from the set separation conditions. So this is a solution. Here I also use an example, a simple example to show you the effectiveness of the proposed strategy. It is a two input for state and two output system with three active actuator modes, one healthy and two faulty modes. Yeah, because we can see two faults, so we need to diagnose both of them. Yeah, the first row of figures is used to show you the diagnosis of the fault one. At the beginning, the initial sets of set-value observers overlap, and we use the proposed logic to design observed gains and inputs and inject them into a system. Yeah, at time intended to 1, we can see that only one step later, the output is only included in the green set. So in this case, it means that fault is diagnosed, and the fault is, the fault 1. During this process, we need a computing time 0.0021 second. And in the same way, we diagnose the fault 2, but this time we need 2 steps to diagnose fault 2, and we also need more time to finish the active fault diagnosis process. Yeah, here also you make a rough comparison between this new logic with the separation-based methods. Yeah, here we look at the results related to the separation results. Yeah, because under the separation framework, actually it has 2 different logic. The first one is that it uses a separation condition to give us a feasible domain where each point inside the domain can be used to separate all sets. So because of this reason, the first simulation is just to find a feasible separation input sequence. And in our simulation, we need 0.7 seconds. And the second simulation is absolutely follow the original optimization program, the quadratic program, to solve mixed integer quadratic program to find the optimal input sequence. And in this simulation, I wait for 2000 seconds. But I cannot get the results within 2000 seconds. So finally, I give it up. So we can see the results here. It's clear that using the new logic, we can reduce computational complexity. But in my opinion, actually here, in our logic, in our framework, we have to lose some performance because we design input step by step. It is a short-sighted idea. And the separation methods design n-step inputs to separate all the sets at a time. It is a long-sighted idea. So in my opinion, our new framework will lose some performance. But till now, we don't make sufficient simulations to compare how much performance this new framework lose. This is what I want to do in the future. Here I just show you the effectiveness to reduce computational complexity. This is the second section of the second part. Follow the proposed framework in the first section in our previous work. We can see that we implement active diagnosis by 2 steps. The first step is to design input to maximize the sensitivity density. The second step is to design observed gains to minimize the size of output sets. But we know that minimal size of output sets does not mean the optimal for diagnosis. So this is our motivation to continue our work, our research. And the next step, we want to further optimize observed gains to improve for diagnosis performance. This is the motivation of our second work. I recall the same scheme using a bank of set-value observers to show you the difference between this work and the previous work. Here we have 2 steps. The first step is to enlarge separation tendency of output sets. The second step is to test if the measure output is inside the output sets or not. they are separate. They are done separately. Yeah. So our idea here is that can we design observer gains to directly exclude unmatched moves, such that 2 steps above can be fused into 1 step? If we can do in that way, it's clear we will be able to improve the performance. In some sense, this is the global solution, and the previous one, we do it separately, is like local solution. So follow this idea. The first question we need to answer is that how can we test if the output is inside the set. Here we have the 4 diagnosis criterion. We test it online step by step. Because if we want to integrate the 2 steps together, we need to transform it into an optimization problem. In some sense, we can design an algorithm to do the 2 steps together. We don't depend on our eyes to say if the output is inside the output set. So based on this idea, we turn to a linear program from Scott 2014. It gives a solution about how to use the optimization program to test if a point out is inside the Zoto. We can say this LP program is originated from the definition of Zotos. So from this LP program, we will realize that the value that hat plays a very important role in judging if the output is inside the output set. Here I show you some conclusions. If that hat is larger than 1, it means the output is not inside the output set. If it's smaller than 1, it means the output is inside the output set. And 1, in some sense, it is a boundary between the inclusion and exclusion between the output and the output sets. So motivated by this phenomenon, here we define a value. We define the value of that hat as the exclusion tendency of output from the output set. So follow this idea. Our method to design optimal observer gains is to increase the exclusion tendency of outputs from each inconstant output set, such that its value increases from a value smaller than 1 to a value larger than 1. In this case, we can exclude the corresponding unmatched output set. Here we can have a look the center and the generate form of set value observers. We can see that both the center and generator metrics are related to observer gains. It tells us that we can optimize observer gains to improve performance. And based on the exclusion tendency we defined in the previous slide, here we can formulate an optimization program, a max mini program. We want to design observer gains to max the exclusion tendency to improve for diagnosis performance. And here, at the below of this slide, we have a figure. It shows the role of the observer gain LFD. It change the center and reshape the shape of the total to exclude the output from the output set. This is what we want to do. I think it's also necessary for us to make a comparison between the 2 different observer gains. In our previous work, we also need to design observer gains, and here we need to design it again. And in the previous work, the idea is to design observer gains to minimize the size. In this way, we can improve the state estimation performance of surveillance observers. And here we design observer gains to boost the exclusion of the output from output set. So the function of two different sets is different. Here I also use a figure to show the difference of the two gains. This phenomenon also tells us that for diagnosis and state estimation are different. Especially they have different requirements on observer gains. In the previous slides, we formulate a bi-level mini-max mini program. But if we want to solve it directly, it will be a little difficult. But we can say that the inner layer of the max mini program is linear. It has strong duality. So based on this idea, we can transform the inner layer into a max program. So finally, we have a bi-level max program, and we can integrate the two max into one max, and we can get a single level max program. That is in the left side of this slide. In this way, if we can solve this program, we will be able to obtain optimal observer gains for diagnosis. But we can say that there are some bilinear terms. If we want to solve it directly, it will be a little difficult as well. So how to solve it? This is our idea here. We transform. We use linear variables to replace the group of bilinear terms. In this case, we can transform the previous optimizing problem into a linear program. Then after we solving this linear program, we will be able to obtain a group of optimal solution, gamma, lambda, and v. Here, lambda and v are the Lagrangian multipliers. And then after we obtain the optimal solution of this optimization program, we can further turn to the equation. The equation between gamma, v, and L to design the observer gains. And in the right side of this slide, we can get the general solution of the observer gains. It also has two parts. The first part is a special solution, and the second part is a free variable. So till now, our idea is that how to make full use of this free variable RK. Can we use it to improve the performance of our observer? In the following, I will show you several ways to make use of this free variable. The first way is to optimize RK to minimize the state estimation sets provided by the set-value observers. Here, the idea is similar with the first work. We use the F radius to measure the size of state estimation sets, and then we can formulate an unconjoined convex program, and we can derive an analytical expression of the optimal RK. We can also use the free parameter to suppress the divergence of state estimation error, and the dynamics of the observer. Till now, in the previous slides, we don't talk about stability of observers. Here we can use this free parameter to suppress its divergence. Based on the near-proof theory, we can formulate a new optimization program here. After we solve it, we can get the optimal value of alpha. Here we use alpha star to represent its optimal value. If alpha star is smaller than 0, it means that the system is stable at least this step. If it's larger than 0, it means that we cannot guarantee stability of observer at this step. But at least, in this way to optimize RK, we can suppress the divergence of the observer dynamics. The third way to improve the performance of observers. The idea is to guarantee stability. Yeah. The direct way to design observed gains that guarantee stability, yeah, is to add a conjoint into our original optimization program. Yeah, then we solve the program, we can obtain observed gains that can guarantee stability. Yeah, here is the optimizing program. Yeah, we obtain, but the problem is that this optimizing problem is also difficult to solve. In our paper, we proposed a branch and bound method to search the solution of this optimizing problem, but it's quite time consuming. So here I want to make a summary, yeah, because I introduced 3 different ways to improve the performance of set value observers in active for diagnosis framework. Yeah. In reality, which one should we use depends on the particular applications, I think. Yeah, this is an example to show the improvement of the observer gain optimization methods. Yeah, with respect to the previous method. In the first 2 rows of figures, yeah, we use 2 different design methods to implement active for diagnosis. Both of them can implement for diagnosis. Only need 2 steps, yeah, to diagnose the fault. And the first method needs 1.5 seconds, and the second method needs 2.6 seconds, yeah, to finish the whole process. And I also use our previous work, yeah, to diagnose the same fault, and we can see that, yeah, it used 3 steps, yeah, but it cannot diagnose the fault successfully. So, yeah, after after we make a comparison of the figures here, we can see that, yeah, by using this new method to optimization of field gains, yeah, we can improve the performance of the whole framework. But the price is that we have to use more computational resources to improve the performance. Yeah, actually, in our original paper, we make more detailed comparisons. Yeah, you can turn to our original paper to see the details. Yeah, here I want to make a conclusions and also introduce you some of our future work. Yeah, in this presentation, I introduced the 2 works of us. The first one is that we proposed a new framework using a bank of set value observers, yeah, to do for diagnosis. And the advantage of this new framework is that it can achieve lower computational complexity. And the second work is that, yeah, follow the same framework, yeah, we finally proposed a way to optimize the observed gains to finally improve for diagnosis performance, yeah, of the framework. In the future, yeah, what I want to do first is to make a detailed comparison, yeah, of diagnosis performance between the set separation methods, the classical methods, yeah, with our set separation tendency-based methods. And because they follow 2 different logic and the frameworks are different, in some sense it's quite difficult to make a fair comparison between the 2 different methods. Yeah, but I also want to do this research, try to do some simulations to give us some new results on this point. Yeah, finally, I want to make acknowledgements to some of my collaborators on active for diagnosis. Yeah, during the past years, yeah, I also supervised several students who work on active for diagnosis, and I also want to make acknowledgement to all of them. And yeah, I also want to thank my founding sponsors. Yeah, thanks for your attention.
Okay, and many thanks, Feng, for your very interesting presentation. And now your presentation is open for discussions. Who wants to start with asking questions? Okay, I have a short list. Maybe I'll start with asking the first ones. Maybe we could go to the slide number 6.
6, right?
Yes.
Okay.
Where you have introduced the system model.
Yeah, wait a moment.
Yeah.
Okay. Yeah.
Yes. Yeah. Yes, what I liked very much is your generalization of a classical multi-hypothesis filtering approach also to the set-valued context. And my question here is it possible for you to deal also with multiple faults in your system? Or do you have to enumerate multiple faults, include them directly in this matrix G?
Yeah.
Yes, that's the first part of my question. And the second part is, what about faults in the output equation? Sensor faults, for example. Is this possible to generalize your idea?
Okay. Yeah, I think it's a good question. Actually, the idea can be generalized. Yeah. Here, I just use the actual faults as an example to show you the logic of the proposed framework. Yeah, we can, for example, yeah, for multiple faults, yeah, we can modify the matrix G, yeah, in some sense. And if we want to consider sensor faults, yeah, we can put sensor fault signature matrix in front of the output matrix C. So we can do it.
Yes, and what about something like common cause failures, that you have a single reason that causes multiple components to fail at the same time?
Actually, yeah, currently, I think for us, yeah, we try to propose a new idea to implement for diagnosis. Yeah, actually, we don't do a lot of research to see its potential to do some other works. Yeah, maybe we can do it in the future.
Yeah. Okay, then no one has unmuted him or herself at the moment. Therefore, I would like to continue a little bit. It was the slide 13.
Slide 13. Okay. Wait
yes,
a moment.
Where you talked about the input optimization.
Okay. This one, 13?
Yeah, yes, here.
Okay.
Your second block, you have said you have a one-step input at a time, but repeated n times. Does this mean that your control input UK needs to equal UK plus 1, UK plus 2, and so on until UK plus n? Or what does this mean exactly?
Okay.
From a practical perspective.
Okay. Here, I mean, the n in the second block is different from the n in the first block. Yeah, they should be different. Here, I just put them. I use the same symbol here. The logic is that, yeah, we design the input. Yeah, at each step to increase the separation degree of output sets. Yeah, and then next step, I continue to design input to continue to increase the separation degree of output sets.
Okay, that means each time step has its own input.
Yes, of course, yes. Yeah.
Yes, because I was a little bit confused when you presented this slide, whether you have a constant input over multiple time steps, or if you mean that you're optimizing in each time step the input and repeat the optimization at each point in time.
Yes. In the first block, in the classical idea, it design an n-step input to separate all output at a time.
Mm-hmm.
Yeah, here we design input step by step.
Yes, and the other thing that I was wondering is you have more or less, it was very nicely presented. You have those two objectives. The one objective is to reduce the, let's say, the width of the size of your estimated sonotope. The other thing was enhance the detectability of your fault by getting the midpoints of the sonotopes as far away as possible.
You mean here, right? Here?
Yes, yes, either this one, yes, that's a nice thing to see here. The other alternative would have been the figure. Yes, but what you have, you want to get the midpoints of the fault-free and the faulty sonotope as far away as possible. And at the same time, you want to reduce the size of the estimated domain.
Okay. Yeah.
There's one thing that you didn't take into account. And I think that's interesting from a practical perspective. I think your control effort is unbounded at the moment. You could get extremely large system inputs, which are maybe not feasible in practice because you're reaching some non-modeled actuator saturations.
Okay, yeah.
What to do in such cases?
Okay, I will reintroduce the idea here. Yeah, we can turn to the previous slide. Yeah, here we want to design the observer gains by solving this optimization problem. Yeah, actually, after we solve it, we can get a general solution of the observer gains. Yeah, it is in the right side, the equation. Yeah. I mean, here we have a free variable RK. Yeah. During this process, we can obtain a free variable. And the next, I mean, in the following slides, I introduce several ways to make use of RK to improve the performance of the server. So this is the logic.
Okay, and that means if you have, for example, in some scenarios, a control input U that would become too fast, you would too large, you would play around with R to compensate this.
In some sense, here in this step, is not it has no relation to the controller. Yeah, we only want to design the observed gain, but the free variable is from the equation. Yeah, when we're solving the equation, yeah, we can naturally obtain a free variable RK.
Okay. Yes.
Yeah. So next, yeah, if we can make full use of this free variable, it will be able to further improve the performance. So that is the logic behind.
Okay. Yeah. Okay, then let me ask my final question that I have on my list, on my piece of paper that I've written down in the meantime. Okay. At the end, you presented the computing times.
Okay, yeah.
Yes, and my question would be, how well does your approach scale also to systems with higher dimensions? What kind of increase of complexity do you expect? And the second question is, what is the most time-consuming part of your algorithm? If someone wants to get, at the moment, you're aiming at an optimal solution.
Okay,
if you want to get it run in real time, maybe, and you're detecting, your 2.6 seconds is by far too large, where to do some suboptimality, maybe, in order to speed up the approach and maybe lose something like the tightness, for example, of the enclosures. What is the most time-consuming ingredient of your approach, and how well does it scale?
Okay, in this example, we only use a very simple example to show an effective list of the results. Actually, we don't do sufficient number of simulations to test. I mean, is computational capacity, especially for large scale systems. We don't do that. Yeah, here I just use the examples to show you that the new logic and framework can reduce complexity, compared with the previous works. If we want to get conclusions, as you mentioned, we need to do more research and more simulations, to get some convincing results on the computing time. That is the first question. And the second one is that I think the most time-consuming part during the whole process is about solving the optimization programs. Okay. Yeah, here the difference that I mean, in the previous work, especially set separation-based work, it's need to solve mixed integer quadratic programs. But here we only need to solve convex programs. So that's the difference. Yeah, of course, the computing time will increase. I mean, if the scale of system increases, despite we only need to solve convex programs. If the system is very large, of course, we need more time to solve it. But we need to do more investigation to know the accurate results.
Okay, then. This was my complete list of questions. Then let's have a look at the audience again. Is there someone else who wants to ask anything? Okay, I see no one having raised the hand, the virtual hand. Okay, if this isn't the case, then many thanks again, Feng, for your interesting presentation. It was a great pleasure having you here and giving your talk. And yes, then to all of you, especially for people in Asia at the moment, have a nice evening. Definitely all of you have a nice weekend. And yes, we'll see each other again next Friday already for the next talk. And yes, until then, enjoy your time and we'll see each other again in 1 week.
Okay, thank you very much. Thank you to give me this opportunity to introduce our work. Yeah, see you next time. Next Friday, right?